Hello everybody, in this video we're going to look at some extra examples for resolution of forces. If you haven't watched the original video on resolution of forces, I suggest you watch that first. You can click on the link right above, or you can click on the first link in the description down below. If you have already done so, let's get to it. So Bob, who weighs 500 newtons, went climbing with his friends and he fell. His friends are now keeping him alive, for now. If the entire system is in equilibrium, what are the tensions in the strings? So the first thing I'm going to do is I'm going to draw out the force diagram. So we can see that Bob has a weight that is going downwards, right? So this is the first part of my force diagram. Weight of 500 newtons going down. I then have a tension 1 going up this way, right? That is tension 1, and that is 50 degrees. To the horizontal. Then I have another tension 2 going this way. So the key point here is to take note of tension 1. Since tension 1 is at an angle, that means I can resolve the force into a horizontal and a vertical component. For example, like this, I can have a T1x, which stands for the horizontal force of T1. And then we have T1y, which is the vertical component of T1. So from here, for now I can just ignore T1. I can just look at the horizontal and vertical components. And since everything is in equilibrium, I know that T1x must be equals to T2 and T1y must be equals to 500 newtons. Okay, so using the second one, T1y is equals to 500 newtons, I am able to calculate what T1 is, because if I go back to the resolution of forces, I know that T1y is actually the opposite line in this right angle triangle. So T1y would be equals to T1 sine 50 degrees. Okay, T1y is equals to T1 sine 50 degrees. Okay, so from here I can get 500, just based on this equation here. 500 newtons is equals to T1 sine 50, and so T1 is equals to 500 divided by sine 50, and this should give me 652.7 newtons. Okay, 652.7 newtons. So from here, using this information, I can now get what T1x is. Okay, because again, T1x is the adjacent line in this right angle triangle. So I know that T1x is equals to T1 cos 50 degrees. And that is equals to 652.7 cos 50. Oops, sorry. Cos 50. So now I will get 652.7, 419.55 newtons. So we also know that T1x is equals to T2. So that means T2 is equals to 419.55 newtons, right? So that is how I get T1, and that is how I get T2. Let's look at the second question. A huge object weighing 50,000 newtons is sliding down a frictionless slope. If the system is in equilibrium, calculate the normal reaction force R and the force of Captain Malaysia on the container, which is F. And as we can see here, the slope is at a 30 degrees angle to the horizontal. Now, the thing to remember about objects on slopes is that their weight, because of gravity, is always pointing downwards. Right? So imagine that the slope is like our normal floor. Then the weight would seem to be at an angle to our slope, right? So we can actually resolve this weight into two components, a vertical and a horizontal component. But in the case of a slope, it is more of a one component that is perpendicular to the slope, right, 90 degrees, and one component that is parallel to the slope, this way, right? So if we move the parallel component down, we get another right angled triangle, like this, and we can also find out that this angle over here is actually equals to the angle of a slope, which in this case is 30 degrees, right? So let me just label the forces here so it'll make our lives easier later. I'm gonna call this the perpendicular, right? Per component of the weight for perpendicular, and W par, right, which stands for parallel. Okay, so if I again compare the forces, I can see that the perpendicular component, which is this way, would be equal to the reaction force, the normal reaction force R, right? Because it's in equilibrium. So at any axis, the forces must be equal, the forces must be balanced. And the parallel component of the weight, since it is on the same axis as F, then these two forces must also equal. Okay, so I'll just make a copy of this over here, sorry. So now we can start doing our thing. So for the perpendicular component, let's look at that. The perpendicular component. In the right angle triangle, it is actually the adjacent line, right? So we know that the perpendicular component of the weight must be equals to the weight itself, which is the hypotenuse, cos the angle 30 degrees, right? So that is equals to 50,000 cos 30, okay, which will get me 43,301.3 newtons. Okay, and remember, since the perpendicular component and the normal reaction force are the same, this is actually equals to R, the normal reaction force. And then the parallel component, okay, that is actually the opposite end of the right angle triangle. So we know that the parallel component is equals to the weight again, which is the hypotenuse, sine 30 degrees. So again, that is 50,000 sine 30, and that will get me sine 30 times 50,000, that's 25,000 newtons. Okay, and we also mentioned that the parallel component is actually equals to the F, the force exerted by Captain Malaysia on the container to keep it in equilibrium. Okay, so that is it for the extra examples of resolution of forces. If you like this video and if you learned something new, remember to give it a like and subscribe to my channel for more physics related content. I'm WeiEn Physics, and I'll see you in the next video. Remember, never stop learning.